Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, the goal is very simple. I just want to work on a problem with you. Okay? Let me show you the problem I would like you to solve with me. Okay? So in this case, we are given the MGF of a random variable y, okay, and using that MGF we have to find the distribution of y, the expected value of the random variable, and then its variance. Okay, let's try and solve part A. Okay, we know that when we see that word, the distribution, right, when we see those words, the distribution of y, what we mean is just we need the list of possible values for the random variable y along with its corresponding probabilities. Okay, that's it, that's what we want. Okay, so let's do part A. Now, how do we go about this? We have the MGF, okay, but that's all we have. How about we recall the definition? Okay, so recall that by definition the MGF of y is given by a particular expected value. The expected value of a transformation. Expected value of e to the power ty. Okay? And let's try and think of this guy in terms of where the probability mass function could appear, right? So we know that the expected value of a transformation would be the sum for all y's of the transformation evaluated at a particular y times the PMF, the probability mass function of the random variable y. So that could be useful because what we want here is that PMF, right? So we have sum for all y's of this transformation, this case, times the probability that the random variable y equals a particular value, lowercase y. Make sense? Okay, so that could be useful. Now let's go back to the MGF we have here. Let's try and rewrite it, okay, and then we're going to compare that to the definition. Okay, so we know or we're given, we know that in this particular case that's our MGF, and as I said, let's try and re-express it. Okay, so this I'm going to rewrite this one like this. To make a direct comparison. So the first term is the same as the first term is 1 over 6 times e to the power t. That's the same as e to the power t times 1 times 1 over 6. Agreed? Second one, I'm going to be doing something similar with the other two. Okay? Let me place this guy here in front. Going to be doing the same with that term, with that exponential. And this e to the power 2t is the same as t times 2. This guy is the same as t times 3. Right? So now let's compare what we have here. We have a sum of 3 terms, 1, 2, and 3, right? And we have e to the power t times something, and then we have a number, a probability, right? Furthermore, note that the sum of 1 over 6, 2 over 6, and 3 over 6, 1 plus 2 plus 3, that's 6 divided by 6, that's 1. And these guys are numbers between 0 and 1. So just by comparing this, the MGF, with the definition, just by comparison, we conclude that the probability distribution must be the following. List of possible values for y. 1, 2, and 3. Corresponding probabilities. Probability of y being equal to 1, 1 over 6. Probability of y being equal to 2, 2 over 6. Probability of y being equal to 3, 3 over 6. And, you know, the list of possible values along with its probabilities gives you the probability distribution. Okay, so let's write that down. So we conclude that the distribution of y is given by, let me write that down like this, y could be, well, y could be 1 or 2 or 3, and the probability that y equals a particular value, y, lowercase y, is going to be, for this guy, for 1 is 1 over 6, for 2 is 2 over 6, and for this guy 3 over 6. And as we pointed out, these three numbers are numbers between 0 and 1, and when you add them all up the result is 1. So they satisfy the two properties of legit probability distribution. Okay? Okay, so we're done with part A. Let's do part B. Let's find the expected value of y. So now that we have the probability distribution of y, well, we could find the expected value using the definition of expected value, and since we also have the MGF of y, we could use the MGF also to find that expected value. So let's do it both ways and check, right? Okay, so one way using definition of expected value. Okay, so here we go. By definition, the expected value of y would be just y, well, the sum of y times probability that the random variable y equals that particular value lowercase y, right? So in this case we have 1 times 1 over 6 plus 2 times 2 over 6 plus 3 times 3 over 6. Then this would be 1 over 6 plus 4 over 6 plus 9 over 6, right? 1 over 6 plus 4 over 6 plus 9 over 6. And then what we have is 14 divided by 6. That's using the definition of expected value. Now, another way. Let's use the MGF. Another way using MGF. So using the MGF, the moment generating function, we know that what we have to do is find the first derivative with respect to t, okay, and then evaluate it at 0, okay? So let's do that. First step, let's find the derivative with respect to t. So we need the derivative of the MGF with respect to t. Let me write it down here. Okay. Oh, doesn't like that. I don't know why. Let me try this again. Okay, so as I was saying, let's find the first derivative of m with respect to t, right? Let me remind you what it looks like. So the MGF is this guy, right? So we have 1 over 6 times et, so it would be 1 over 6 et. That would be the derivative, right? So we have the derivative of a sum, that's the sum of derivatives, right? So then we have 1 over 6 e to the power 2t, so constant times the derivative of this guy, the derivative of e to the power 2t would be e to the power 2t times the derivative of this with respect to t by the chain rule, but the derivative of 2 times t with respect to t is just 2. So in the end, what we're going to have is this times 2. Right? Okay. Finally, we have something very similar here. That's the last term, and it would be that constant times e to the power 3t times the derivative with respect to t of 3t, which is going to be just, 3. Okay. So let's simplify that expression. So now instead of 2 here, we're going to have a 4. We can get rid of that guy. Instead of a 3, we will have a 9. Oh, sorry. Okay. Finally, we evaluate at 0. We evaluate at 0, and we know that by doing that evaluation, we will get the expected value. So let's just see what happens when we evaluate at 0. So we have e to the power 0, e to the power 2 times 0, e to the power 3 times 0, right? So in the end, what we have is 1 over 6 plus 4 over 6 plus 9 over 6, right? And, well, that happens to be 14 over 6. Right? And that is the same that we obtained using the definition of expected value. Right? Okay. So we are done with part B. We found the expected value. Now let's find the variance. So at this point, right, we know that if we want to find the variance of a random variable, we have a few options. We could use the definition of variance, which is the expected value of y minus mu, the whole thing, the difference y minus mu squared, right? We find the expected value of that. That's the definition of variance, right? Or we have this theorem, this alternative to finding the variance, which is the variance of y equals the expected value of y squared minus the expected value of y, the whole thing square. Okay, so let's use the second choice, the alternative formula for the variance, not the definition. Okay, so we know that variance of y equals expected value of y square minus expected value of y, the whole thing square. Okay? Okay. So, let's do this one. We already have the expected value of y. So finding the expected value of y squared, no problem. So let's try and find the expected value of y squared. Okay, so expected value of y squared is just this. it would be similar to what we had here, right? By definition, let me borrow this guy. So it would be 1 squared, that's the transformation, right, times the probability of observing a 1, the transformation evaluated at 2 times the probability of observing a 2, and finally transformation evaluated at y equals 3 times the probability that y equals 3, right? Okay. So this will be 1/6 and then we're going to have 4 times 2, that's 8/6. Then we're going to have 9 times 3, which is 27/6. So this will be 36/6, right? Okay, let me leave that like that. Why? Because we have this, the expected value of y happens to be 14/6, so we're going to be squaring that, so it might be a good idea to leave this like that. Okay? Okay, here we go. So this variance of y, which we know is the expected value of y square minus the expected value square, right, is going to be 36 divided by 6, right? Let me write it down like this: 36 divided by 6 minus, and we have 14, right? 14 divided by 6, that's expected value. So 14 divided by 6, that squared. Okay? So let's find that. Let's use R. So 14 square, it's 196, and so that's going to be 196 divided by 36. Let me write that down. This one remains like that. The other one is going to be 196 divided by 6. 196 divided by 6, right? The common denominator, by 36, sorry. The common denominator here will be 36. So it's going to be 36, but we're going to have to multiply 36 by 6. So 36 times 6, that's 216. 216 minus 196. That's 20, right? So in the end we have 20 divided by 36. Okay. Well, we could simplify that a bit more, but let me leave that like that. Okay. Let's use the MGF. Anyway, I mean, we could find that. So roughly, that's what we would have. right? Let me leave it like that. Okay, so as I said, the other way of finding the variance is using the MGF. Okay, so let me just say that. Let's find the variance using the MGF. Let's find variance of y using MGF. Okay, here we go. We know, right, that the MGF is going to give you moments of a random variable with respect to the origin. Okay, so just like we found the first moment with respect to the origin, and that happens to be the expected value of the random variable, it turns out that if you want to find the expected value of y square, you can use the MGF to find that expected value. And let me remind you that the expected value of y square using the MGF of y will be just the second derivative with respect to t of the MGF. So m double prime. Okay, and again remember that we're doing the derivative with respect to t, and we have to evaluate it at 0. Okay, here we go. So from it was part B where we found the MGF, right? Let me say that. From B, right, we will need the MGF. We have it here. Okay, we have the first derivative of the MGF, right? Well, the MGF was already given, so we found the first derivative of the MGF, so we will need the second derivative. So let me copy paste this guy. That's the first derivative. So we have this, and that was just the first derivative. First derivative with respect to t was that. Okay, let's find the second derivative. Let's copy paste this, it will be useful. Let me modify that. Now we want double prime here. So the first derivative of the first term in that sum, 1/6 et, is that guy, right? Now we have a constant times e to the power 2t, right? So it's going to be this guy times the derivative of 2 times t, right? Which is just going to be 2. Okay? This guy, well, a constant times e to the power 3t is going to be this same guy, and by the chain rule, the derivative of 3t with respect to t, and that is going to be just 3, right? Okay. So what we have in the end, let's simplify that, is 8 here. We don't need that 2 any longer. 3 times 9, 27, right? Okay, finally, to find that expected value that we want, we need to evaluate that second derivative we just found at 0. Let's do that. So e to the power of 0, that's just 1. E to the power 2 times 0. E to the power of 0 again, right? So in the end, the expected value of y squared will be 36 over 6. But that's the same thing that we obtained, you know, using the alternative way of finding the variance. We use the distribution of y to find the expected value of y squared. So we're going to end up with the same for the variance. Okay, so let's summarize what we did here today in this video. So in this case, we were given the MGF of a random variable, and we wanted to find the distribution of y. If we have such a situation, there are two possible cases. One, it turns out that we are able to recognize that particular formula that defines the MGF that we're given. If it's a famous formula like the one for Poisson or for a geometric or a binomial, we know that by the uniqueness of MGFs, then y, if the MGF of y looks like the MGF of a binomial, then the distribution of y must be binomial, and then all we have to do is figure out from the expression what are the parameters of that particular value, random variable. Okay, so that's one possibility. The other one is, like in this case, we're given the MGF, but the MGF is not one of those famous popular distributions. So what we did in this case is just we compared the definition with the expression that we were given to find the distribution of y. Remember that the distribution of y is just a list of possible values along with its corresponding probabilities. Something else that we did here is using the MGF to find the expected value, which is the first moment with respect to the origin, right? And we also know that the MGF could help you find other moments with respect to the origin, right? So what we found here was the expected value of y squared, or some people refer to that guy as the second moment with respect to the origin of the random variable y. Okay, so we just used the MGF to find a higher moment with respect to the origin, and that's another application of MGFs. Okay, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.